To continue with semi-definite programs, we're going to see that conformal rigidity has to do with spectral embeddings. That's the goal, okay, for the rest. So, as I told you before, this is a big subject, semi-definite optimization. It takes like many weeks to actually learn it properly. So, I'm just like telling you a lot of things that some of them are just coming at you without any proof or anything. But hopefully at least you see this type of math exists and what it can do, and you have some exposure to it. Maybe that's the only goal we can have for such a short amount of time. And then tomorrow I will need some of these concepts. Tomorrow I'm going to talk about graph sparsification, which is kind of a fresh topic, but you'll see that spectrahedra show up there. So it's nice to know what they are already. Okay? All right, so I'm going to continue with that philosophy. I'm just going to tell you a bunch of stuff, okay? So one thing, so let's look at the semi-definite program that we had. So this was infimum of C transpose X subject to A0 plus sum of Xi AI, I from 1 to M is PSD, okay? And let me call the value of this infimum P star, okay? So this was a semi-definite program for us, good? Okay, so every convex program, in particular semi-definite program, has a dual program, okay? So if we had time, I would derive for you where the dual comes from, but since we don't have time, I'm just tell you what the dual is, and we'll see the connection between the two. If you know linear programming, then you've seen duality there. You know that there are some really great theorems like strong duality, you have complementary slackness and all that, okay? Anyway, don't worry if you don't know it. But the dual program is another semi-definite program. We're going to call it D star. And this is the supremum of the following inner product. So I need to define what this inner product is. So let me write it. Subject to the condition that AI inner product Y is equal to Ci for I from 1 to M. And I have that Y is PSD. Okay? So this is another problem. This is called the dual program to that program, okay? So what's this inner product? Let's talk about the inner product for a minute. So if I have two symmetric matrices A and B, so remember space of symmetric matrices is a vector space. You agree with that? If you add two symmetric matrices, it's symmetric. If you scale a symmetric matrix, it's symmetric. Okay, so it's a vector space, and then inside this vector space, remember, so this is some vector space, and inside the vector space we had this PSD cone. This was Sn plus. So as I told you before, you should think of Sn plus as the non-negative orthant of Sn. Okay, so we had that cone. So now there's an inner, because it's a vector space and it has an inner product that it has many inner products actually you can define. But the standard one is called the Frobenius product. So this is the inner product. And this is by definition the sum of Aij, Bij over all I and j. Okay, that's the definition. So what you're really doing is you're taking your matrix and you're just like unraveling the rows, right? You take all the rows and just make it into a long vector. Do you agree? So take each row, and instead of like the rows being this way, just put one row after the other row, you get a long vector. Do the same for B, and then take the usual Euclidean inner product. That's what's happening, okay? This is called the Frobenius product, inner product. So it has a name, so this is the Frobenius inner product. And this is basically just treating the matrix as a long vector in Euclidean space and taking the usual dot product, okay? Now, maybe you can check that this is the same thing as taking the trace of A times B. So let's leave this as an exercise. So if you multiply A and B together and calculate the trace, which means you sum up the diagonal entries, you also get this, okay?
Transpose.
No, these are symmetric.
Oh, symmetric.
These are symmetric matrices, so you don't need to transpose them, okay? So in general, you do have to transpose them. if you're taking the inner product of two matrices, but these are symmetric matrices. Good? So if you don't know this, please check. Okay, so this is check, that this is the same. Okay, so that's the inner product we're talking about here. All right? So let's go back to this thing and just look at what's happening. So I'm starting with some data. So the data that I'm starting with is, for the primal problem, I have the C vector. So C is part of the data. And then A0 up to AM is part of the data. This is in SN. C is in RM. Okay, so that's the data of the primal problem. This is called the primal. And this is called the dual. Okay, and so that's the data we get. And then from that data, we're constructing another problem where it's the same A0 and AI that's getting used, but now there's a new variable called Y. Okay, so there the variables were, so here in this case, the variables were, in the primal, the variables are x1 through xm. And in the dual, the variable is y. So in the dual, the variable is y, which is required to be a PSD matrix. Okay, that's actually one of the constraints on it. Okay, so actually let me not write grade A equal to. So this is a symmetric matrix. Okay, so this is in the dual, maybe different color. Yeah, okay. Is this all right?
So for the dual also we have C and A1.
Yeah, so using the same data as what that one came with. The C's are used again, the A's are used again, but there's a new variable Y, that's the only new thing. And this new variable must have the property that its inner product with each of the AI's is CI, which is the number here. And you want to take the supremum of minus A0 dot Y, and Y has to be PSD.
Yeah, but there we had the variable x1 to xm. Here, I mean, the data is the same.
Data is the same. That's the key point. Okay, data is the same, but we have one set of variables for the primal and a completely other kind of variable for the dual. For the dual, it's a matrix. That's the variable. For the primal, it's x1 through xn, which is xm, which is a vector. That is the variables. Everybody okay? So it looks a bit like magic, but there's kind of a reason where this comes from. Okay, this is called the dual problem. Okay, so let's first of all maybe understand a little bit about the two problems. So maybe before we do that, let's put back the example that we had. The example we had was infimum of x plus y, subject to this. This is the example with that bubble. So this was x0y, 0y, and then 1 minus x, 1 PSD. Okay, so this was the prime. Suppose this is the primal problem. Can we write the dual? Let's write the dual for this problem. Okay, so you have to tease out what all the matrices are, right? So the C vector is 1, 1. I'll write this out. The A0 part we had before. This is 1, 1. And then there is an A1 part, which is and there is an A2 part. Okay, so that's all the data that's coming with the primal problem. So now I want to construct the dual, which is a soup, first of all. Okay, and then let's just write it like this to begin with. Right? So first of all, I need to set up this Y matrix. How big is the Y matrix? Yeah, it has to be 3 by 3 because it has to dot with some things that are 3 by 3, right? So the Y matrix is, let's number it nicely. So I'm going to just call it ABC, BC, DEE, F. This is the Y matrix. And of course, this has to be PSD. That's the bottom condition. Okay? So can you see if you can write out all the other stuff? So A0 has to dot with this Y.
That is minus D minus F.
Yeah.
No, minus D minus.
Yeah, you need the negative of A0. Yeah, minus D minus F. Does everybody see this? Yeah, so dotting a vector with another vector just means that you have to go entry-wise and look at ij thing there, ij thing here, multiply together, sum it all up, okay? So this is minus A0 times this one, so it's minus D minus F. Is that okay? So this becomes minus D minus F. That's the objective. Please ask if you're confused. Is this okay? Any question? Is that clear? Okay. So then let's see what the other ones are. So that's the first constraint. And then we have to dot A1 and A2 with Y as well and make it equal to Ci. Okay. So let's dot A1 with Y. What will we get? Yeah, so this corresponds to A minus E minus E. Okay. So I get A minus 2E is equal to 1, which is C1. The next one is 2C equal to 1. Okay. Is everybody okay? Did you get what's happening? Okay. So this is what's happening. Okay? So, oh yeah. Sorry. All right. Yeah, it's not that C. Let's put a, okay, I don't want to put a bar on this one. Let's put a bar on that one. Okay. It's not the same C. It's a different C. Okay? Okay, so maybe I'll erase this. You know what that is. Okay. All right, so this one is pretty easy to solve, right?
No, but you also need Y there.
Yeah, you need Y PSD. Yeah? But we can already solve a little bit because 2C is 1, right? So this part tells me that C is half, okay? And then the other one we don't know because A minus 2E is 1, we don't know what's going to happen. So what happens is this Y matrix, we can fill it a little bit. So in the C part, I will get half and half. And then A is equal to 1 minus 2E. So I can write this as 1 plus 2E. So that's A. And then B, we don't know anything about it. And then D, we don't know anything about it. And E is here. And then F is here. So what I need is this has to be PSD. Do you agree? Okay. So we killed off A and we killed off C, but we're still left with E, B, D, F, right? 4 variables. So unlike in that first picture, I'm not going to be able to draw a picture. Do you agree? For the primal problem, we only had 2 variables, X and Y. So we could draw a picture in the plane, you saw the bubble and all that. But this, whatever it is, if you start writing all the principal minors are greater equal to 0, it's something that lives in 4-dimensional space. So we can't really draw a picture easily. Everybody okay? So for this, we need software to actually solve this. You can play with it. It has probably many solutions, but I mean, this is all that we are left with right now. Actually, we also want to do this, right? We want to maximize.
That's confusing me. Because from the principal minors for the 1 by 1 principal minors, we'll get D is greater than equal to 0 and F is greater than equal to 0. And so we are
but that's okay.
Supremum of minus D minus F.
Yeah. But there are more conditions, right? So, so example, DF is greater equal to E square. And then there's more conditions coming from here.
And
right?
E is also greater than or equal to half.
Yeah, E is greater equal to half.
E is, no, 1 plus 2E is greater than equal to 0.
Yeah.
Greater than equal to minus half.
Yeah. Yeah, so there's, it's not exactly linear. So when I write all those PSD conditions out, you will get something that's going to bound the how big D and F can get. Otherwise, the supremum won't work out, right? It's true that D is non-negative and F is non-negative.
So minus, I mean, if I just do the obvious thing, then 0 is the answer. Because
0 is a answer, maybe, but we don't know if that's going to make the minus D minus F as big as possible. Yeah? So there are probably infinitely many ways to fill in this part so that it's PSD, but then among all possible things, we want this. We want to make this D minus F as big as possible.
no, I mean, it cannot be larger than 0, right? Because E and F are both.
Yeah, it cannot be larger than 0. It cannot be larger than 0, right? But so we want to make either, yeah. Everybody okay? This is the dual program. Okay, so now let's look at this program on the computer because we can't draw pictures, so we're going to have to solve this using software. Yeah, okay, it's come. So let's take a look. So this was the problem that we had before. This is the primal problem that we saw before. We saw that its feasible region looks like this. We also we optimized it and we got this point here to be the optimal solution, right? And if you remember, the optimal value is minus 0.23818. Okay, that was the optimal value of the primal problem, right? That's what this told us, and it makes sense, right? It's like down there somewhere, so that's the optimal value. Okay, so now in this next piece, let's put it at the top, what I'm calling CNSTS2, I'm going to enter all the principal minors of this. Okay, so please check, I got them all. So 1 plus 2E must be non-negative, that's the 1 by 1 minor. D is non-negative, F is non-negative. And then I have D times the 1, 2 minor is D times 1 plus 2E must be greater equal to B square. Yeah. And then the 2, 3 minor, DF is greater equal to E square. And then the 1, 3 minor, F times 1 plus 2E is greater equal to 1/4. And I have the whole determinant. I took the determinant of the matrix, it has to be non-negative, right? And then I ask to minimize. So remember, taking the supremum of minus D minus F is the same thing as taking the infimum of D plus F, okay? So I'm asking you to minimize D plus F, subject to those constraints, and the variables are B, D, E, F, because we got rid of the A and the C. And then again, it gave me some garbage, but then when I put N in front of it, I got exactly 0.238, okay? But remember, you have to put that minus sign in the front. So when because I changed soup to inf, okay? So the dual is really soup of minus D minus F, but I wrote it as inf of D plus F, but then I need a minus sign in front, okay? So the answer came out to be exactly, it's really minus of this. So the answer is exactly the same as the value of the primal. Got it? So this is the miracle of duality. Okay, so duality is going to give you at least, well, we'll see that it's not always going to be equal, but it's in this example, the primal value, which was minus 0.23, becomes exact, which is an inf problem, becomes exactly the same as the soup problem, has the same optimal value. Okay, but they're not related in the sense, I mean, that problem is living in 4-dimensional space, this problem is living in 2-dimensional space. They're in different dimensional spaces, okay? So they're not like cone dual and stuff like that, but they are related to cone duality, the picture that we saw before, okay? So you see that, and these are the optimal values of B and D and E and F, okay? It tells you.
These values probably don't have anything to do with those values, only the 0.231.
Yeah, exactly, only the 0.23818. And we'll see that there is a connection between the values as well, but it's not the obvious one, okay? Okay, so that's one way to solve this problem, right? Write all the principal minors out, ask it to minimize. This is not going to work if you have even a 10 by 10 matrix. It's too much work to write out all the principal minors, okay? So Mathematica will allow you to directly solve this problem without writing principal minors. So what I do is I take the matrix M, this matrix that we had, this is the matrix of the primal, you see it? So I enter the matrix as is, okay? And then after I enter the matrix, I'm solving the primal, I ask it to do semi-definite optimization, x plus y, that is my objective, right? For the primal, the objective was x plus, so you see in line 11, so I have a command called semi-definite optimization. It's going to now recognize that this is an SDP. I ask it to, objective is x plus y. And then then there is this funny looking command, which is just saying that this matrix is PSD, okay? So what's the command? It's vector greater equal M0 semi-definite cone, okay? So that means in the semi-definite cone, I want M to be greater equal to the 0 matrix, which is saying, in that order, in the curly order, okay? In the loner order, I'm requiring M to be greater equal to 0. So this is some syntax that you got to use. So all I'm plugging in is semi-definite optimization, x plus y, and then this M is PSD. That's what I'm trying to give it, okay?
So this is the primal code.
This is the primal. And then it solves it. It gives me back the x and y value. It doesn't give me the objective, but we can calculate it, just add it. Okay, so that's great. And then I also do the same thing for the dual. So here is the dual matrix that we had here in pink. This is the matrix. And then I'm just asking it to do semi-definite optimization. So this always assumes it's a min problem, okay? So Mathematica will always assume it's a min problem. So I'm minimizing d plus f. I needed to maximize minus d minus f, but I'm minimizing this, subject to this M dual. That's the pink matrix being PSD. And I get back all the values of B, C, D, E, F, B, D, E, F, and you can check. That's also correct.
But the values don't match.
I am not getting, so the x and y values and the b, that's what you mean?
I mean, if I take x plus y, I will get something less than 0.2.
It's
Because
minus 2.8. That's the answer, right?
minus 2.
Yeah, the answer is minus 0.28, right?
No, it was 2.1.
23818 is with a minus sign in front.
In the dual. No, I'm talking about the primal.
Yeah, the
Primal, it was 0.23. Oh,
no, it was minus 0.23818, right? Remember, this is the picture.
okay.
The x plus y thingy is, so it's minus. In the dual, I have to remember that there's a minus sign in front,
So
which
it's exactly the same.
exactly the same.
Not up to sign.
No, in this case, it's exactly the same. Okay?
Yeah.
So this is how you would want to solve. So Mathematica is not the most sophisticated way to solve an SDP. There is like dedicated software for SDP. So you should, if you're solving some big thing, you should go to a different software. But for small problems, it's really convenient. You can just do it in the same. Yeah, Lavanya.
When we feed in the M dual, we have to compute all the AI dot y, all the inner products, and then with the final value, the
Yeah,
as an input.
No, you can actually also input it in that original form. Okay, you can. So there are all these, in like regular software for SDP, there are wrappers. There are not wrappers, what do you call them? Like interfaces that allow you to input the problem in the most natural way it comes to you, and then it'll do all the pre-processing. It'll compute all the things that we have been computing by hand. Okay?
Which one is better, the final or the dual?
It depends. Okay, so in this example, we went from 2 variables to 4 variables, so looks like the primal is better, but it can be any which way. It depends. People only input the dual? Yeah, so it doesn't, technically they're the same. Okay, you can put either, and
There's some complexity analysis of these two, like time efficient.
yeah, so in principle, these are all, you can solve them in polynomial time up to some epsilon error. Like if you say that the error, these are done by interior point methods. The solution comes by, it's an analytic procedure. So you don't exactly get the optimum, you get close to the optimum. And if you allow epsilon error, then technically this is polytime in 1 over epsilon as a function of that. So, but there's a lot of, it's kind of an open problem, I think, whether the feasibility question is even is a polytime thing. So there's some complications. It's not as nice as linear programming, okay? So anyway, so this is just the very, very basic stuff. Okay, great. So this is how you would do it, okay? But now I'm going to show you why the values were the same and why this is good and what else we can get from it. But before I go there, let me just show you this thing, which is super cool. So Mathematica now has an entire class called conformally rigid, okay? So this is from our paper from last year. And the people at Mathematica now have inside graph data. So these graphs are all conformally rigid, okay? It will be somewhere down here. So there it goes. There's a lot of graphs that are conformally rigid. They're complete. And it won't be all completes. It'll be some of them. Complete bipartite. So we were very thrilled to see this, that they actually put this inside graph data. So all these graphs are conformally rigid. It's pretty cool. Anyway, all right, so this is, so the person who did this is also the person responsible for your licenses. So we should thank him, right? So he contacted us after we put the paper up, and he computed one example that we couldn't compute because they have supercomputers that can do very large examples. So he computed something that we couldn't compute. And so we had this exchange with him some time ago. I don't know if it's here. Forget what the name of that graph was. But it had 120 vertices, and we couldn't quite do it with our laptops. So then when this Gyan course came around, I wrote to him and said, hey, can we get Mathematica licenses? And here we are. You all have licenses. Okay. So, yeah, there are lots of very cool graphs. If you go in our paper, you'll see some really interesting graphs. And there are some graphs for which we know they're conformally rigid, but we don't have a proper explanation. There's no theorem that's saying, oh, it's because of this theorem. It's just computationally true, and we can verify it as well. With the edge transitive. These are, yeah, probably some there are some edge transitives in here, but the interesting would be, class would be when you're outside edge transitive, outside distance regular, outside one walk regular. Those we can theoretically prove are conformally rigid, and also some Cayley's, right? But there are even more ones that we don't know why they're conformally rigid, but they are. Okay, so there's some nice open problems there. Let me show you one more thing before we close the computer. Okay, so these are pictures of spectrahedra. This is how spectrahedra look. Okay, so all polyhedra are spectrahedra, but these are some pictures of three-dimensional spectrahedra because that's all we can draw. So you see they look like this. Okay, this is a very famous one. This is called the elliptope. This is the set of our correlation matrices from statistics. This is a spectrahedron. So that just means xii equals 1, x PSD, like the type we saw in the MaxCut. But these are all spectrahedra, and there's lots of good questions about their geometry that we don't know. Unlike polytopes, we don't know too much about spectrahedra. We know a lot, but not a lot. Both. Is it okay? Okay, so these are pictures. Okay, so let's shut this down. Yeah?
Something out of context, why are they called spectrahedra?
I think, so it was named by somebody called something Ramana, who studied this in the 90s. And I don't know what, I don't remember the first part. No, he's an optimization person. In the 90s, I'm not sure, I don't know where he is now. But he called it spectrahedra because it really depends on, it's about PSD matrices and so on. I don't know if that's the best name, but that's the name that has stuck. Okay, they call spectrahedra. Because the PSD-ness is about eigenvalues, right? It's really about eigenvalues being non-negative. Okay. Okay, so let me tell you two more facts about these. The primal and the dual, okay? So the first thing is something called weak duality. Which claims that if X is primal feasible and y is dual feasible. So that means x is something that satisfies these constraints and y is something that satisfies these constraints. If you pick a point in this spectrohedron and a point in this spectrohedron, x and y, then it must be that C transpose x, which is the inf objective, is always greater or equal to minus A0 inner product y. So the inf value is always above the sup value. Okay? So in the primal problem, so this is a very, very important fact. So in the primal problem, we have the C transpose x, we are trying to push it down, right? We're trying to minimize it. In the dual problem, we have this minus A naught y, we're trying to push it up. And it's saying that they'll never cross. The min value of the, or any value of C transpose x will always be greater than any value of minus A y, okay? So they'll never cross. They'll approach, but they'll never cross. And in the example we just saw, they become equal. That's called strong duality, okay? So this happens, and sometimes you'll get strong duality. So this was, so this implies in particular that P star is greater or equal to D star. Do you agree with that? Because for any x, this is true. So for the lowest x, it's going to be greater or equal to the biggest. So the lowest value of this is going to be greater or equal to the biggest value of this, right? So I will get that if I put inf, so let's write it. So this fact implies that the inf of C transpose x over such that x is primal feasible is going to be always greater or equal to the sup of minus A0 y. And that implies that P star is always going to be greater or equal to D star. This is called weak duality. Okay? This one is not hard to prove. So you can just look at the situation and figure this out. So you have to use the fact that, so let's see, can we prove it quickly? So what I need to prove is that this minus this is greater or equal to 0, right? That's what I got to show. So let's see, maybe we can do it. Right, so let's look at C transpose x plus exactly A0 y. So I need to argue that this is greater or equal to 0, right? So this side minus this side is greater or equal to 0. That's what we got to show. So I brought this to the other side. And now I have C transpose x plus A0 dot y. Let's work with this. So what is this? So this is so C, where's C? So Ci's, remember, is AI dot y. Okay, so I can substitute for that. So this is AI dot y, which is a number, okay, times xi, exactly. Sum, that's what the C transpose x is, right? Because this piece is Ci from here, okay? So I have that plus A0y, okay? So that's what this is. So the top one is this, everybody agree? I just substituted for Ci. Ci is inner product of AI with y, okay? And now combine them. So this is equal to, so this is a number, right? This xi. So I can pull it and make it close to this AI. That's okay. So this becomes A0 plus sum of xi AI, okay, inner product y. Do you agree? I skipped a bunch of steps, but yeah? So what am I doing? So this is some sum, and this is another sum. This is a bunch of inner products plus another inner product, right? This xi I can bring to the inside and stick it here. So I have AI xi inner producted with y, sum, plus A0 inner producted with y. So I combine it together and say I want all this to inner product with y. A0 inner product y plus inner products will work like this, right?
So
okay.
And both are PSD.
Exactly. So what we know, since X is primal feasible, this is PSD. And Y is also PSD because Y is primal, dual feasible. So both these are PSD matrices. And I'm taking the inner product of two PSD matrices, right? And this is always non-negative. So this requires a proof, okay? So let's leave that also as an exercise. So this is always non-negative. And what we're using is exercise. Show that if A is PSD and B is PSD, then it implies that the inner product is always greater or equal to 0. Does anybody see quickly how to do it?
Trace of AB, right? So A eigenvalues of
Yeah? I got half answers. You have an answer? Okay, you want to make the spectral decomposition of A and, let's just do the blue thing, because that's a general one, right? So in the general one, A is PSD, so it can be written as U sigma U transpose, or U lambda, A maybe, lambda, and B can also be written as V lambda prime, V transpose. This is the spectral decomposition of both of them, okay? And the lambda is a diagonal with non-negative diagonal entries because these are PSD matrices. So what happens when you take the inner product? Okay, so we can multiply the two. So let's use a trace definition maybe. Yeah, so what happens if you do AB? So AB is U lambda, U transpose, V lambda prime, V transpose. Okay, and then can you get rid of something? Oh, I need the trace of this. Okay, so I need the trace of this, which is equal to the trace of this. Okay, good. Good. Now trace is cyclic.
trace of AB is
Yeah, so exactly. So you can rotate things around inside trace and it won't change things. So I could move this U to the other side, okay? This is another fact. So there's lots of facts. So this is lambda, U transpose V, lambda prime, V transpose U, okay? And then what do we do?
U transpose V transpose is V transpose U.
no, if we make U transpose this side,
You want to take V transpose that side?
V this side, U transpose this side.
Okay, so let me leave this to you because we have a long way to go still today, okay?
Instead of diagonalizing and using V, if we just rotate in the basis for U,
Okay.
then we would have then lambda dash is not diagonal, but from there
Okay.
we could
All right, let's try Soam's idea. So you want to write B as U times some matrix, right?
is denoted by lambda prime.
Okay, but it's not diagonal, you're saying? And then,
U transpose.
okay. And now I still have this trace AB.
And, but one notice is that lambda prime is still a PSD.
This is PSD. Ah, okay. Okay, so this is PSD. And then what happens if you take the trace? So I get U lambda, U transpose U, lambda prime, U transpose. This is what Soham is saying. And then this cancels. This is the identity. And then this becomes trace of U lambda, lambda prime, U transpose. And then we can move this here and cancel it out, right? Because these are orthogonal matrices. So this comes to this side and cancels out. So we are left with trace of diagonal with all positive things in it and something PSD. Okay, so you can finish this, okay? So anyway, this is a fact. This is non-negative. So this is the proof of weak duality, what I just showed you, okay? So what we just argued is that if you add this to this, you get something non-negative. And I think this may be an exercise, maybe not, that this blue thing is the exercise. That if you take the inner product of two PSD matrices, it's non-negative. Is this okay? All right, so That's one fact, okay, weak duality. Then the next fact is sometimes you get them to be equal. P star will become D star, and that's called strong duality. So strong duality.
So weak duality is always true, but strong duality is not always.
Exactly. So this is always true. Weak duality is always true, and strong duality if P star is D star. So in the example we did, we had strong duality. That's why we got the two values to become equal.
Have trace of lambda, lambda prime. One of them is diagonal.
Correct.
Other is for
PSD.
So then the product will be also diagonal.
No. The diagonal lambda will multiply the rows, right? You'll scale the rows positively. And then you have to maybe think a bit more.
Then you have to take the trace and you have to show that the trace is positive.
Yeah, exactly. Yeah, exactly. So you will, from lambda is something diagonal. So it's going to scale every row of lambda prime, right? And then we are taking, then you'll get some lambda double prime. And we're taking the trace of that. So we're just summing up the diagonal elements, which are positive because we just scale them positively. Maybe differently, but positively.
How do we know that lambda prime is PSD? Because oh, it's just a change of basis.
Yeah, it's a change of basis, but it's not the spectral change of basis. Yeah, some change of basis. Okay, very good. Thanks for that help. Okay, everybody okay with this? So sometimes you have strong duality and then you have, okay, we have all that. Okay, so let me state the very last thing and then I want to show you how this relates to conformal rigidity and then we're done. Okay, so as I said, I'm really telling you a lot of things that takes, entire classes to explain properly. So you're just sort of seeing a glimpse of it, but hopefully you see that these things exist. Okay, so the last thing I want to tell you, last result, is that, okay, so there's also there are theorems that guarantee strong duality. Okay, so maybe I won't worry about that. But let me tell you the last big theorem, which is called complementary slackness. So again, if you know linear programming, you know what this is. But let's just write this statement. So suppose you have strong duality. So suppose P star is D star. Okay. And X star is the optimum of the primal. And Y star is the optimum of the dual. So it can be sometimes that there are optimal values, but there's no optimal solution. SDP is sort of weird. But let's take the nicest case, okay? P star is D star, the two things agree, and I have an optimal solution little x star for the primal and the optimal solution Y star for the dual.
Sorry, under what conditions do we have strong duality?
So I didn't write it, but there are conditions. So for example, if this problem is strictly feasible, meaning that there is a choice of xi's that makes this side positive definite, then you get strong duality. Or if this is strictly feasible, you get strong duality, okay? I don't think you need both to hold. Let me just check. Yeah, if either one of those holds, you get strong duality, okay? If both hold, you actually get that P star, D star agree, and the optimal solutions also exist. Okay, these are called Slater conditions. So it's a kind of, the trouble happens because of low dimensional things, like when the feasible region becomes low dimensional, it has no interior, that's when problems start to happen. But if this is strictly feasible, that means this has an interior, right? There are positive definite things inside here, then you're okay. Similarly here, okay? So there are these things called Slater conditions, which I didn't write. But let's suppose we have P star is D star.
Like yesterday there was this bee sticking out of the something like that. Because it's not falling on that hyperplane, all the bees.
Yeah, it really has to do with the existence of interiors. Okay, that will happen.
Natural things will satisfy.
Natural things will satisfy. And the lambda 2 maximization that I just wrote before, like maximizing lambda 2 W in a graph, that satisfies strong duality. Okay? So that's one of our exercises to argue that it satisfies strong duality. But it's a very nice LP. It has SDP. It has P star equal to D star. It also has optima and all kinds of stuff. Okay? It's the nicest kind of SDP. Okay, now I'm going to write something that maybe you'll complain about, but let me write it anyway. Okay, let me write the statement. So X star is optimal for the primal, Y star is optimal for the dual. Okay? So if all this happens, then if you plug in X star into the pencil, so remember this is the pencil, okay? This is A0 plus sum of AI Xi star. And then this is a matrix, right? This is an n by n matrix. And you multiply this with Y star, which is also an n by n matrix. This is multiply, not Frobenius product. Multiply. If you multiply these two together, you will get the zero matrix. Okay? This is called complementary slackness. This is a very cool fact. I can prove it to you right now that this will happen. But you need P star to be D star. You need optimal solution for the primal, optimal solution for the dual. Then when you plug in X star into this piece and multiply it with the Y star from here, you will get 0. Okay, do you want to see the proof? Yeah? Okay, so let's quickly prove it. This is actually fun to prove. It also needs a little exercise, but we can try it. Okay, so P star equal to D star means what? P star is equal to C transpose X star, and this is equal to D star, which is minus A naught Y star, which is equal to D star. This is our assumption. We have this equality. Okay, by assumption we have that equality. Okay, so then what happens if I take the inner product of AX star with Y star? Let's start with this. Let's check the inner product, not the product, but the inner product. Okay, let's compute this. So this is given. We're given that P star is D star, so I have this equality, so now I'm going to check the inner product, okay? So this inner product is equal to, what is this? A0 plus sum of Xi star AI inner product Y star, right? I just wrote out the AX, the pencil part, okay? Then inner product distributes over sum, so this is equal to A0 Y star. I can take the inner product with just this matrix, and then I can do plus sum. Yeah, and I can even pull the Xi star out, and then I have AI inner product Y star. Everybody okay?
Y star is minus D star.
Yeah, AI inner product Y star is C star, right? It's the, you see?
Yes.
It's CI. So this bit over here is CI. Yeah? Good?
And that is minus D star.
Exactly. So this is equal to, this is minus, so this is equal to minus D star. And this is equal to, this is CI, these are Xi stars. So this is equal to C transpose X star. So, and that is P star. So altogether we have minus D star plus P star. Okay? So that inner product is minus D star plus P star. But what is that? That's 0, because we are assuming P star and D star are the same. Right? So that is 0. So it tells you that the inner product of this pencil with this is 0. Okay? Now exercise, if the, yeah, it's in the notes. So in the exercises, if PSD matrices, so remember both are PSD. This is PSD, right? Because this is feasible. If two PSD matrices have inner product 0, then their product is 0, which is very, very strong. Okay? This you can prove with the spectral decomposition. Just write down the spectral decomposition. So the exercise here is, so we have two exercises. Oof, terrible blue. So the two exercises are that if A and B are PSD, first exercise was that their inner product is non-negative. Okay, and the second is that if the inner product is 0, then it implies that the product is 0.
So also BA is 0 because it's an.
Yes, I guess so.
And it is one-way implication. Converse need not be.
Yeah, probably. We just need this direction. Okay? All right, so there are lots of things about PSD matrices that we're using here. It's all coming at you in like 2 hours. I apologize, but hopefully at least you see the big things, okay? So the big things to remember are what's over there. Primal, dual, weak duality, sometimes strong duality. If strong duality, complementary slackness.
Why is funny name? Complementary.
Because in the LP case, it really is like a complementary slackness. So it's saying that if, so the primal problem will be like this, right? This grade A equal to BI. That'll be the constraints. And in the dual, there will be some variables YI. And what you'll get is that this difference times the YI is 0. It looks like this, okay? And it's saying that either this is 0 or this is 0 for the optimal solution. So either a constraint is tight, if this constraint is not tight, if there's really slack in that constraint, so the optimal solution is here, and let's say this constraint is this one. So if there is slack, then the corresponding Y variable has to be 0. So you get a lot of control on the dual solution from knowing whether there's slack in the optimals. It's very, very, very powerful, this complementary slackness, okay? You can use it for lots of stuff. Okay, so I'm going to give you, let me give you the punchline, and depending on how much time we have, we will work backwards, okay? So what I want to argue to you, okay, we have all the statements now. This was a proof. Okay, so now I'm going to, if I had time, I would do this in a linear order, but I'm going to do this in reverse order right now. So let's write the theorem, and then we'll go backwards. Okay, so we saw that the lower conformal rigidity is this problem, right? Minimize sum of the Wij's subject to LW grade A equal to I minus 1 over Nj, W non-negative. This is an SDP. So this is some primal SDP. Okay. And this primal SDP has a dual SDP, which is in the exercises, okay? This dual SDP I won't even write. So there's a dual SDP, which we can write if we have time, okay? So let me just tell the story of what's going to happen, okay? So we have this primal SDP, which we derived very carefully this morning. It has a dual SDP that you can just write from that recipe, okay? That's easy. Then you have to check that this really has strong duality, okay? So you have to check that it's, you know, one of the problems is strictly feasible, it has strong duality. So P star is D star, so we can do complementary slackness, okay? So so everything nice happens for this problem.
For any graph.
For any graph, any connected graph, this will happen, okay? So this is the primal, there's a dual, there's strong duality, there's complementary slackness. Everything happens, this takes some time, you can check it, okay? Then at the end of the day, when you analyze what this complementary slackness condition is telling us, it is telling us that the graph has to be embedded in a very special way on the eigenspaces. Okay, that's what complementary slackness means. So all I need to do is to define what these embeddings are, and then I'm going to write the theorem. So let's define what a spectral embedding of a graph is. So spectral embedding of G on the eigenspace with eigenvalue lambda. This is what I'm going to do, okay? So pick an eigenvalue, pick its eigenspace. I'm going to define what it means to spectrally embed the graph.
So are we assuming weighted or unweighted?
Unweighted. Let's assume unweighted, okay? All right, so what you have to do is you have to pick some eigenvectors from this eigenspace. So, I don't know, we'll call them something else. Yeah, let me call them phi. So there is some phi1. This is not the first eigenvector, that's why I don't want to use that notation. Let's pick some eigenvectors from this eigenspace. So let's say I pick k of them. They're independent and all that, okay? So the dimension of this eigenspace is greater equal to k, greater equal to k. Yeah, E lambda. Okay, so this eigenspace has some dimension. Pick a bunch of independent eigenvectors from there, okay? So this gives me some matrix, right? So these columns are the eigenvectors. So this is going to have size n by k, n by whatever, k. Good? And now, because there are n rows to this matrix, there are n rows here, right? And they're living in k-dimensional space. So let's call the rows, I don't know, P1, P2, up to Pn. This is the last row, okay?
So just to clarify, P lambda has dimension k or greater than it?
It's at least k. So I'm picking k independent eigenvectors from that eigenspace.
And you're assuming orthonormal?
You don't have to for the actual definition, but yeah, let's go ahead and assume they are orthogonal. But you don't have to. The definition works with whatever. Okay? So pick those, and you have these rows. Good? So now use these rows as the position of each of the vertices. So go to Rk and put vertex 1 at point P1, put vertex 2 at point P2. So the rows are giving us an embedding of the vertices. Okay? So these rows are not living in the eigenspace, remember, okay? The eigenspace elements are the columns. So it's like duality from yesterday. So eigenspace elements are the columns, but there are n rows. So use those n rows to embed your graph. Okay? Put your vertices on those points and connect all the things that should connect. Okay? The edges are easy once you know where the...
And we should respect, so the vertex number 1 should go on.
Yes, you should respect order every time in this week. Next week you can do whatever. Okay? So in this, so take the rows, use them as the points for the vertices, okay? This is what we did if you think when we did clustering. Remember in that very easy algorithm, we took the Fiedler vector, which is one eigenvector, this is phi2, and we said I'm going to put vertex 1 wherever this number is, which is on the real line. And then I put vertex 2, whatever that number is, this is where vertex 2 goes, then this is vertex 3, and so on, right? This is a one-dimensional embedding. This was a spectral embedding, the one that we saw with clustering. Here I'm just using more eigenvectors, so I get a higher dimensional embedding. Good? This is called a spectral embedding. Okay, spectral embeddings are super nice. You can look at pictures from Dan Spielman's book, for example. He has a draft of a book on spectral graph theory, Dan Spielman from Yale. And you'll see that these embeddings are super nice, okay? If you actually embed the icosahedron graph spectrally, it looks like an icosahedron, okay? So they're very nice. There are many, many types of nice embeddings. This is one of them. Okay, and now we're going to call, so I didn't write everything, but everybody got it? So we're using these rows to embed the graph, and then add the edges, okay? Draw all the edges, straight lines. That's fine. Okay, so we're going to call this embedding edge isometric if after you draw in all the edges have the same length. Good? So I'll add that definition. So spectral embedding means, so embed G by sending by sending vertex I to pi. This is the embedding, okay? And we say that this embedding is edge isometric if after you finish embedding, the norm of pi minus pj, so remember this is where vertex I is, this is where vertex j is, this is the length of the edge that connects the two. This norm is a constant for all edges. It has to be a positive constant. Okay, so all the edges end up having the same length. That's called an edge isometric embedding, which is very rare. You're not going to always get this, right? So P's are whatever, and then you connected all the edges, and if all the edges ended up having the same length, we call it edge isometric.
But there seems to be a lot of freedom here.
If with what? Yeah, there's a lot of freedom. It's up.
You choose which lambda, you choose the k.
Yeah, so there's an entire orthogonal group action you can put here.
But you're also allowing yourself the freedom to choose k instead of taking.
You know, so I'm saying I'm not choosing any. I'm just let's fix the eigenspace, and let's do this.
No, but then k also is free, right?
That's also free. Yes. Lots of freedom. Lots of freedom. Agreed. Okay.
We are embedding the k-dimensional space.
Yeah, we are embedding in a k-dimensional space. So it could be we chose only 2 eigenvectors. It could be we chose the maximal number of eigenvectors. Yeah, lots of freedom. Okay, this is spectral embedding. Edge isometric is clear? All right. 6 minutes. So let's write the theorem. So the theorem is that, okay, now we have to connect the dots backwards, but maybe that's homework or for some other time. So the theorem we proved, this is Steinerberger and me, what we proved is that G is conformally rigid. You can also tease this apart and write lower conformally and upper conformally if you want. If and only if G has an edge isometric embedding, on the second eigenspace and the last eigenspace. That's the result. Okay? So this is an equivalent way to look for conformally rigid graphs. So you should go to the second eigenspace and see if you can find an embedding that is edge isometric. And you should go to the last eigenspace and be able to find an edge embedding that's edge isometric.
So presume lower conformally rigid has to do with lambda 2 and upper.
That's right. So if you only wanted lower conformally rigid, forget about this one. If you only wanted upper conformally rigid, forget about this one. Okay? Is this okay?
And is it enough to just take k to be
the full thing? Yeah, it's enough. But yeah, it's usually enough. And many of our constructions use all freedom. And the place this comes from is from here. From here. Okay? So there's lots of ... between here to there. Okay? So what happens is, so let me just summarize the story. So this is how you minimize lambda 2. This has a dual. Okay? Dual has strong duality. It has complementary slackness. So you get this thing out of it. Okay? And if you look at this very closely, it's exactly saying that. It's saying that there's an edge isometric embedding in the eigenspace of lambda 2. And similarly for lambda n, there is a similar different SDP. It also has a dual. It also has strong duality. And if you analyze complementary slackness, you will get exactly that this means there is an edge isometric embedding. Okay? So now do you see why, let's see, is there an easy one? So maybe bipartite graph is easy. So for a bipartite graph, the last eigenvector is like 1 minus 1, 1 minus 1, and so on. So that means there's only one typically. So that means you can put all the vertices either at 1 or at minus 1. Okay? And all edges will go from 1 to minus 1. This is a fact that you can think about. So that means all edges just go between 1 and minus 1 for a bipartite graph. That's a spectral embedding that is edge isometric. Okay, so some simple ones you can see quickly. This is a good technique for the circulant question I asked you. All you have to know is, can I take the circulant graph and can I take the circulant graph and embed it into its second eigenspace? So second eigenspace of circulants with two generators is two-dimensional. So it's really an embedding into R2, but it's not just any embedding into R2. It really has to be a spectral embedding, okay? They're not the same as just arbitrarily embedding in R2. So you're being asked if I can take my circulant and take all the edges and, wrap them in some ways so that all the edges have the same length. Okay, so
just to relate with something else. So in 2 dimensions, so if you can embed a graph such that all the edges have the same length, these are called isoradial graphs.
Okay.
So
it's similar. Yeah, this is spectral embedding is more special than just a embedding into the correct dimension. So that I think in our second paper we give an example to show that they are different. They are more special. But if you have it, then that's exactly conformal rigidity. Okay.
So are there graphs for which there is no edge isometric embedding whatsoever on any lambda, any k?
Yes. Okay. Yes. There are also graphs for which there are edge isometric embeddings in every eigenspace. That's these one-walk regulars. Oh. These one-walk regulars, distance regular, they have an edge isometric embedding in every eigenspace, not just lambda 2 and lambda n. Right? So it's kind of all over the place. Okay, I'm sorry a lot of stuff came at you today, but hopefully you saw like one arc of math that's connected to math, right? So, to graphs. So we started with graphs, and then yesterday we saw polytopes, Gale duality, and how you do designs with them. Today you saw lambda 2 optimization, lambda n minimization. It's connected to semi-definite programming. So that was one of my hopes with this course, that you see connections to many different parts of math. So that's today and yesterday and today. And then tomorrow we'll talk about sparsifiers, which is a lot lighter. But you do need to know what a spectrahedron is, which is why I wanted to introduce that object today. So in the morning tomorrow, we'll talk about how to sparsify a graph. So that's yet another new topic. And that's the last one. All right, great. That's it. That's it for today.